So without further ado, I think Max can start on bronze problem one.
So I'm going to be going over the first problem of bronze this contest, roundabout rounding. I assume that most of you have read this problem already, but I'll just give you guys a quick refresher. So basically, the problem defines regular rounding as just like rounding by the first digit. So if you want to round to the nearest power of 10, for example, like 449 would round to 100. But chain rounding, as the problem defines it, just rounds like by digit from right to left. So like 449 would be rounded to 450, and then that gets rounded to 500, and then that gets rounded to 1,000. And the deal is basically what it's asking you is, given you a number n, you want to find how many numbers between 2 to n will round to different powers of 10 when chain rounding compared to regular rounding. Yeah, so here's the example input. We have like four numbers: 1, 100, 4, 5, 6, 7, and 3, 3, 6, 6. I won't be going over like the later two samples because they're just too big. But like, yeah, for 1, obviously there are 0 numbers between 2 and 1 because 1 is less than 2. But for 100, the numbers that satisfy this condition are 45, 46, 47, 48, and 49. So these 5 numbers will first round to 50, and then 50 gets rounded to 100. But if you round it normally, they'll just round down to 10. And then for 4, 5, 6, 7, and 3, 3, 6, 6, yeah, the numbers are really big, but trust the sample input. That is, in fact, correct. So this is part 1 of the solution. The key observation is to that basically only numbers between like 4, 4, 4, 4, 4, and so on, and like 500 and so on, like not inclusive by the way, will round differently when chain rounding versus regular rounding. I have, I guess, this example written now. I'm not gonna read it out because it's a lot of numbers, but yeah, you guys get the idea. Like all numbers between like such patterns will round differently when chain rounding versus regular rounding. Any numbers below that will just round down when in both cases, and any numbers above that will round up in both cases. Yeah. And then, yeah, the way to deal with this is just you quote unquote looped over like each power of 10. So basically, like, each possible like length of a number in digits, I guess, in other terms. And then you would count the numbers between like 4, 4, 4, 4, and like 5, 0, 0, 0, 0. And for that like digit length or power of 10. And you also want to make sure it's less than n. So I guess specific casework is like if n is less than 4, 4, 4, 4, then you're done, right? There's no new numbers that fulfill the condition. Everything you're going to be looping over from now on is going to be greater than n, so it won't work. So you just like terminate the loop and output your answer. Otherwise, if n is like greater than a number, then what you do is you add this statement, like you add the minimum of n and like 49999 minus 44444 to the answer. Yeah, the logic is that basically for like this digit length, this power of 10, there's gonna be like 49999 minus 4444 numbers in this power of 10 to fulfill the condition. But you also want to make sure that they're less than n. So yeah, if n is less than 49999, then like you do n minus 4444 and so on. Does anyone have any questions on this logic? All right, if not, in that case, I'll just hop into, I guess, a live implementation. So yeah, I'll just hop into implementation. So I'm just gonna read in the input real quick. We're gonna input the number of test cases they give us, and then we loop through it. And then we're gonna use a long for our n here. The reasoning is for this is that we use long because the number has 9 digits, and like 4 times 10 to the 9 is actually greater than the int limit. There are certain implementations that can definitely bypass having to use long, but in this case, I find that it is just safer to do it anyway. In USACO, honestly, since you get unlimited submissions and no penalty, it won't really matter if you get a wrong answer, but it is a generally good idea to know when to use long and when to not use long. I've seen some people just say like define int long and do that. Personally, I would not recommend doing that. It slows down your performance and is generally like bad code practice, but it is also an option if you guys are really lazy and just don't want to know when to use like long or not. But yeah, let's just actually write the code now. So I'm going to define a number called like, I guess, left bound. That's just going to be like 444. And then we're going to like define a number called right bound. That's also going to be 4 initially, but this is going to be like 499. we're just gonna loop through each power of n, initialize our answer as 0, I guess. So while left bound is less than n, because if n is less than or equal to left bound, then we just end the program. Then we add minimum of n and right bound minus left bound. So like minimum of n and like 499 minus 444, and you add that to the answer. And then we're gonna update our left bound and right bound to like add another 4 or another 9. So we're just gonna do like times 10 plus 4, and for right bound, since it's gonna be like 499, we do times 10 plus 9. I think that should be correct. Let me just output that answer real quick. See if this works. Okay, it does work.
Hi everyone. We're going over bronze problem two. So again, hopefully you're familiar or like read the problem, but I'll quickly explain the problem first. So essentially, Farmer John has a block of cheese, and this is the cube of side length n. It extends from 0, 0, 0 to n, n, n. So again, we're in the 3D coordinate plane. And n is at most 1,000. And so essentially, there's Q updates that are happening, and each update, he's taking out a one by one piece of a block, um, and it basically extends from x comma y comma z to x plus 1 comma y plus 1 comma z plus 1. And these coordinates are between 0 inclusive and then at like less than n, because um, if it was equal to n, that would go past the block, sadly. So essentially, after each update, you're trying to find um, how many ways can Farmer John insert a one by n block, uh, or I guess brick, such that it doesn't intersect any of the remaining cheese. And all of the coordinates are between 0 and n inclusive. And by all the coordinates, I mean all 8 corners of the block. And the block may be rotated. So you could do one by n. You could also do one by n by 1 and n by 1 by 1. So let's look at a sample case, because because the problem is, I guess, a bit weird to understand when you initially read it. So in this case, you have a 2 by 2 by 2 block. Initially, so this one has it's a tube, it's like a cube with side length 2. So you first remove the bottom leftmost corner. And this is probably better with the visual, so annotate. So you have a 2 by 2 by 2 block. That's right. And then you have like 4 cubes in the top layer, 4 in the bottom layer. It's kind of hard to draw it out, but something like this. Okay, that one looks pretty close to what the thing looks like. Okay, so in the first move, you remove like this bottom left block, so this is gone. Then you remove the top right block, so this one is gone. Um, and then you remove the block that's right here. So this two, and notice that after removing the third one, so initially the first two answers was 0. That means like you can place a one by n block anywhere. But after you remove this third block, this segment right here, it's a little bit hard to see, but this is actually a one by 2 block, or a brick, I guess. Since you're removing 2 adjacent cells, you could like insert a one by 2 block here, and that's where you get the answer of 2, or sorry, of 1, because that's like the only way you can place it. The next one you remove is the one back here. Again, this is kind of hard to see, but I guess for the bottom row, you can view it as like a 2 by 2 grid. For just looking at the bottom row only. So initially we removed 0, 0 on this grid. Then we removed 0, 1, which is right here, and then now we're doing 1, 0. So this is a one by 2 block. This is a one by 2 block. That's where you get 2 from. And then the fifth one, or sorry, the fifth one gives you 3 more one by 2 blocks. This one's kind of hard to visualize adding it, but essentially it adds to 2 of the bottom ones. Like you get 2 more from the bottom one, and also you can form a one by 2 with this top right corner right here. So again, it's kind of hard to visualize, but if you draw it out on like, if you think about the bottom row and the top row separately, it's much easier. So looking at the sample, this kind of leads to some basic questions. Um, First of all, if a one by one brick was able to be inserted at some update, can it ever be like not insertable on a future update? And the answer to this one is pretty clearly no, because we never like add back a cheese block after carving it out. Once we carve out a cheese block, it's carved out forever. So if we were able to place a one by n block somewhere, at some point in time after like everything's been carved out in that area, well, we can always place that one by n block. Um, and using this information, this actually gives us the answer is always non-decreasing. Essentially, it can never like decrease from one input to one query to the next one. It's always going to stay the same or increase. You can see that pretty clearly in the output. It's always like increasing or staying the same. It's never decreasing. Um, and also, what's the maximum possible answer to a query? This isn't actually really easy. Um, if you think about it like geometrically, there's three different arrangements you can have of a block, as I mentioned earlier. Um, so if you remember, it could either be like one by n, it could be one by n by one, and or it could be n by one. So let's think about like how many ways are there to place a block of each type on the cube. So if you have a one by n block, yeah, you can think of it as placed like one column down. And so there's n squared ways to do that because if you think about the top face is the n by n grid um, of the cube, and each one by n block shares exactly one cell at the top, and they're all distinct. So there's n squared of these. And by symmetry, all the other like the other two arrangements also give you n squared. So the answer to the third question is that there's 3n squared at max. And this is actually the main observation that's going to help us solve the problem. And we'll be looking at this a little bit more in depth in a future slide. But yeah, this tells us that the answer is actually not cubic in n. It's always quadratic, which is really important because if you look at the constraints, n is at most 1,000. So even storing the cube n by n grid would be too much memory since that's 10 to the power of 9. So and this question is also super important. How many one by n bricks is any unit cube part of? So if you think about it, like if you have a single unit cube, uh, the like for okay, so if you consider any three of these one of these three arrangements, it can be part of exactly one of them. So if you consider one by n, it can't be in two different one by n's since they all share disjoint blocks. Like they can't intersect obviously because they're if you think about it like one column and a second column, they can't like share any cells. So this one can be at most one of these, and it's exactly one actually because each cell or each block is part of at least one of these bricks. And same for this one. So this one and this one. Essentially, we figure out that uh, any unit cube can be part of at most 3 bricks. And we don't even say at most, it's exactly 3 bricks because for each of them, each block fits in exactly one. So this actually gives us a naive solution. I think this was 1 or 2 subtasks. I don't remember clearly. But essentially, after each update, there's O of n squared possible bricks that can be inserted, as we showed on the previous slide. Specifically 3n squared, but that constant is pretty small and doesn't matter. So there's O of n squared possible bricks that can be inserted. After each query, we can simply just check each of these bricks, and for each of the n blocks in that brick, just check if it's been removed yet. So storing the blocks that were removed, you can do this with like a map in C++ or a hash set, or you can just make it through n by n array, which would be fine in this case because well the solution is already O of n cubed q, so you don't have to worry about n cubed being too large for memory since any solution that like had a n cubed q solution in terms of time complexity should pass n cubed in terms of space complexity as well. So again, this solution is over n cubed q because for each query you would have to check each of the n squared blocks or bricks, and then each brick has n blocks to check as well. So how do you optimize this? It's the idea is that for each brick, we can maintain how many of the n blocks inside that brick have been carved out. And the reason, like the way this is motivated is because it's kind of repetitive to check each brick after each query. Like you don't really need to check all of them. Like if some brick had like and again the observation in the first slide, if some brick already hit that n benchmark of like n things being carved out, you really don't need to check it again, since it's gonna work again, and that's just wasting time to check it and add to your answer, even though it's already been counted in the previous answer. Um, so for each of the three n squared bricks, you can maintain how many of like the n blocks in it have been carved out. And so the way you do this is just by storing three arrays for each of the three types of bricks. Notice that for each type of brick, there are n squared different bricks that actually have that type. So 3n squared in total. And so if you store this in three at 2 by n bit arrays, you can like again store how many of it have carved out. But again, how do you effectively make sure like update the answer? Because currently that looks like an O of n squared Q solution. The idea is again using that last observation we had on the first slide. It's that each query changes this value. So by this value, I'm referring to how many of the blocks in each brick have been carved out. It only affects the value of 3 bricks. And the reason for this is because each unit cube is part of exactly 3 bricks. So each query affects 3 bricks. We can update the value of these 3 bricks in like O of 1 time, basically, because you're just calling an array and I'm changing its value. And if the value of that brick is now n, essentially meaning that everything in it has been carved out, we add 1 to our answer. And so notice here that we're keeping the same answer from the previous query. We're actually just changing it based on like how many new bricks are available to insert. And that allows us to like finish. And so this final complexity, it's not listed here, but it would be O of n squared plus Q, because the initial initialization of the 3 arrays storing all the bricks takes n squared time. Updating each of the bricks takes O of 1 time for each query. So that would be O of Q time for processing all the queries. So we can now look at implementation. There's actually a lot of ways to implement this. I think this one is definitely the easiest and most like I guess clear on what's going on. So I'll explain the implementation. So initially we just take the input of n and q. So that's just the size of the cube and the number of queries. Then we're initializing 3 arrays. So these variables are kind of indicative of what the array represents. So this one represents where the x and y direction are the ones, so 1 by 1 by n. This is going to be 1 by n by 1, and this is going to be n by 1 by 1. So that, yeah, again, that's why you have x, y, x, z, y, z, depending on which directions we're changing. And again, we make a answer variable that's initially 0. This is global, so it stays the same, like it's being used, like it's updating like cumulative across all the queries. So for each query, we're going to take the input of x, y, and z, which are again the coordinates of the block we're removing. And this is a part that it's just like figuring out like what brick corresponds to like each of the directions. So if you're looking at the unit cube from x, y, z to x plus y plus x plus 1, y plus 1, z plus 1, in the x, y direction, the coordinates are x, y. Y, z direction is y, z. X, z direction is x, z. So essentially, we add 1 to indicate that in each of these like bricks, we're carving out 1 more cell. And if they've hit that new benchmark of n, then you add 1 to the answer, and then you print it out. So you have to do this for all 3 bricks. So the reason again this works is because the only bricks that could possibly be new, in the sense that like the ones that didn't work in the previous test case and now work, are the ones that are formed through this unit cube. So yeah, that's the solution to the problem. Does anyone have any questions about this one? All right, that's it for this problem.
The rough gist of the problem is that we're given a string of went then, and all the letters are alphabet characters. And a moo is defined as any substring of 3 characters where the last 2 characters are the same. So, like for example, moo, is classified as a moo, while mom is not classified as a moo here. I can go on more examples, but I think the definition is clear enough. And then you have to print in sorted order all the possible moves that could appear at least f times in the string, considering that up to n, considering that up to 1 character in the string may be altered. So, I'll go over some samples like to make this idea a bit more clear. Okay. Yeah. So, in okay. So the first sample. Sorry. In the first sample, the only moo is moo because even if you make one edit, you can't make zoo or any other moo, occur more than 2 times. However, in the second example, if you change one of the z's to an m or one of the m's to a z, then you can make moo or zoo occur twice. Okay. So we have to know a few things. So first, there's only 26 characters we can choose from because all the, letters in the string are alphabetic. Second, n is somewhat small, it's 2 times 10 to the 4. And third, there's not that many like moves possible. There's only around 676 possible moves. So, uh, this gives us a lot to work with. So here's one of the ways to do it. So we can basically brute force on every possible corruption or like every possible like character that we change. Yeah, the issue with doing this and just bashing it out though is that recomputing the frequency of each move would take too long. That would be O of n squared, which clearly times out. Okay, so from now, what we have to notice is that editing a given position I will only affect 3 moves, the ones at I minus 1, I, and I plus 1, if we consider moo I to be the one with like the middle character at I. But yeah, so like if we go back, if we like change this here, like the third character in the first example, then that would only affect character 2, character 3, and character 4 in terms of possible moves that could be affected. Okay, so yeah, okay, so for each possible edit, we want to see if it changes the maximum number of times any given move will show up. Each edit only affects 3 possible moves, so we just need to account for every move that no longer exists after the edit, and also the number of moves that we added after the edit. And then for each of the newly added moves, we check that if the edit made it show up at least f times. If so, then we know that, this move could have been made by Bessie. Okay. I'm gonna pull up the implementation. Can you guys see my code? Uh, okay. I'll just go over the implementation. If you guys can't see my code, let me know. Yeah. Uh, so we initialize an array for each of the possible moves and how many times it shows up in our current string. And this table is to just like keep track of the maximum number of times a given move shows up in any given string. So first we read in the input, nothing too special here. One thing I did here was convert every alphabetical character into a number from 0 to 25. That just makes it easier to implement because that means we don't have to deal with maps or anything like that. Okay. Then in this block of the code, we're just initializing both the frequency table and the maximum frequency table to just account for any of the, possible moves that already show up if we don't make any edits. One thing to note is that a moo, like in a moo, like all 3 characters can't be the same. The first one is supposed to be different from the second and third, but you'll see later that this does not matter in the implementation. Right, so in this section of the code, what we're doing is we're just brute forcing on each of the possible character changes. So, in our frequency table, we first like remove all the previous moves that were there when we did not make the edit. So yeah, we just have like a small loop condition here to check that, and if the condition is true, then we update it. So for this block of the code, what we are doing is that we are replacing the character in our array, and then we're just checking if that changes the number of moves that like show up. And then over here, we kind of update the maximum frequency table to see if the number of moves or the maximum number of times this move has showed up increased. And then we're just like we're just undoing like all of the changes we made in this edit so we can proceed with our iteration. And then finally, we just check the maximum frequency table for each move and see if and then like we just see if each given move like is valid according to the problem's conditions. And one thing to note is that because we're iterating the first character in alphabetical order and then the second one in alphabetical order, we don't actually have to sort this array, which is nice. But yeah, that's it for me.
The problem essentially states that we have an even length array of cakes with sizes, and we have two players, Bessie and Elsie. Now what Bessie does is that Bessie can merge two of the cakes on her turn, and then after that Elsie eats one of the cakes on the ends. And when there's only one cake left, which is always like I think Bessie will act twice in a row or something, but when there's only one cake left, then Bessie will eat that cake. Yeah. If this isn't so clear, we can go over the samples. I guess for the first sample, what Bessie will do is Bessie should merge cakes 30 and 40. So after this becomes 40, 50, 10. Afterwards, Elsie will probably eat cake 40, so resulting in 50, 10, and Bessie merges these two cakes, resulting in Bessie getting 60 and Elsie getting 40. And then you might notice that for the second sample, it's the same, just reversed. And because both operations are symmetrical, we should not be surprised that the result is the exact same. When we're starting to do this problem, we can notice a few things about the structure of it. The first is that Elsie, because Elsie always eats from one end or the other, what Bessie takes at the end must be a contiguous segment of cakes. What this means is that like, given that Elsie will eat like let's say like 3 times from the right and like once from the left, that leaves this segment with Bessie, and that it's pretty clear that like it's not possible for Elsie to eat like over here or something because she would have needed to eat all of these cakes first, meaning that Bessie's final taken segment will be a subarray of the original array. When dealing with problems like this, it's often educational to like add some constraints or deal with subtasks first. And the first one is particularly interesting. In particular, the first subtask is when all sizes are equal. What this essentially means is that we no longer care about the size of the cakes, just the quantity of cakes that Bessie and Elsie will eat. I guess another thing that we can observe is that Elsie will always eat n over 2 minus 1 times, and this just results from the fact that the cows alternate doing operations, and but on the last cycle, I guess Bessie will just take both of the cakes remaining. So you can kind of see that demonstrated here, where Elsie ate once, and 4 divided by 2 minus 1 equals 1. And clearly Elsie only ate one cake. So yeah, I suppose that if you're Bessie in this case, then like our wishful thinking is that maybe we can only force Elsie to just take n over 2 minus 1 cakes, and then you can take the rest. And it turns out this is actually something that we can do. We can realize that because Elsie eats n over 2 minus 1 cakes, she can never reach the middle 2 cakes. What I mean by this is that let's say like Bessie only moves once. This isn't like necessarily true of the problem, but it is I guess it's educational assumption. Given that Elsie only eats the given that Elsie only eats n over 2 minus 1 cakes, she can, if she just focuses on eating the left side, she can reach cake n over 2 minus 2, I believe. Or no, sorry, n over 2 minus 1. Given that she focuses on eating the right side, she can also reach like n over 2 plus 1, but she can never reach but if you like merge these two cakes, she can never reach the stuff in between. Thus, I guess like in order to force Elsie to only eat this many cakes, Elsie can never eat a quote unquote merged cake. So that's the first move. We just merge the middle 2 cakes. And then afterwards, we want to maintain this distance so that Elsie can never actually reach the edge of our of the block we're creating essentially. And this way, Elsie, and to do this, we can just mirror Elsie's moves. To give an example of this, let me erase this. We can just first we merge the middle 2 cakes. Then let's say Elsie takes this cake for herself. Then we want to maintain like the proper distance. So instead of going closer to Elsie, which would result in Elsie being able to take this in the end, we mirror her move and merge this farther away into here, which maintains this equal distance of n over 2 minus I and n over 2 minus I. Thus, we are this is pretty much a uh invariant of the problem where because we're able to maintain this distance, Elsie can never reach your block you're making, and you can force Elsie to only eat n over 2 minus 1 cakes, where Bessie will eat n over 2 plus 1. So that is a solution for the first subtask, and this idea actually seems pretty powerful. So we should try to make it work for variable cake sizes. Using a previous approach, we know that Bessie can always take a subarray of length n over 2 plus 1. And given that we stick to this strategy, it's also true that now from the point of view of Elsie, if we know that Bessie's going to follow this, then Elsie can always force Bessie to pick the minimum subarray of length n over 2 plus 1. This is because, like in our previous approach, Bessie always mirrored Elsie moves. So for example, if we wanted to force Bessie to like take this subarray or something, we can just eat until we go here and eat until we go here, no matter what Bessie moves, and then that will force Bessie to do this. I don't think this is too hard to see. Then I guess given this, right, we can ask the question, is the strategy optimal for Bessie and Elsie? On one hand, for Bessie, clearly Bessie cannot eat more cakes, but then we also want to prove that Bessie can't eat higher value cakes. The intuition for this is that as soon as Bessie, if Bessie does not follow the strategy, Bessie will let Elsie eat a merged cake. And the problem with letting Elsie eat a merged cake is that essentially takes one of Bessie's moves and gives it to Elsie for free. And then Bessie doesn't, and then Bessie merges one less time, which results in a strictly worse outcome. And then given that this is the optimal strategy for Bessie, since Bessie will always take an array of length n over 2 plus 1, Elsie will try to force that array to be the minimum array of length n over 2 plus 1, because if it's not minimal, then she could have taken more. If you want to formally prove this, I believe you can induct on the length of the array, but to keep this editorial brief, I won't go into that. So thus, Bessie will just get the minimum subarray of length n over 2 plus 1, and Elsie will get the rest of the array. You can do this with like 2 pointers or prefix sums, and that should be pretty simple to do. For some code, this is not too hard. You just maintain some you just maintain the array and then run like a pretty standard 2 pointers to get the solution. Does anybody have any questions on this problem whatsoever? Yeah, okay. If not, we can go over the second problem. This problem is called deforestation, where a TLDR of it is that we have n trees that exist at these coordinates, and we have k requirements. Now, given these k requirements of there be t trees in LR, we need to find the minimum number of trees that can satisfy this. I believe that in the original problem statement, it's actually like the maximum number of trees you can delete, but these are trivially equivalent problems. When you first look at this problem, I suppose that something good to keep in mind is that like perhaps this is some sort of greedy problem. What motivates this is it's actually similar to a lot of other like really standard problems that hopefully you guys have seen. If you have not, I'd recommend you to go to Music Guide and look at them. But first one is CSCS Movie Festival, and the second one is task and deadlines. And if you've seen those problems, this problem will look quite similar, albeit a bit more complex. Now, a thing that these two have in common is a common idea of sorting by the right endpoint of an interval. And this is just a common idea in like interval satisfying problems. And the intuition behind this is you want to sort of procrastinate. You want to use your trees as late as possible so you don't waste early trees. The pretty much the scenario we're trying to avoid with this is if we have something like if we have two intervals like this and this, we want to make sure that when we take a tree, and if there's a tree here, we always want to take a tree that covers both intervals. If this tree exists, we don't want to take this tree over here, realize that we don't have a tree to cover the second interval, and then take like another tree here. That'd be really bad. So pretty much by sorting by right endpoint, we first just encounter here, say, oh, let's take the last tree, and then realize that for this guy, we've already satisfied it. So to like go over that again, if this interval, so we can sort intervals by right endpoint and then go through them increasingly. And then if an interval still requires k trees, we take the latest k trees within the interval to satisfy it. And then we can move on to the next interval. I guess if you still need like a more rigorous proof, you can read a handout on the exchange argument. We'll be sending out the slides later so you guys can look at that, but hopefully you have enough intuition to go on this approach. However, problematically, even with this greedy, our solution is still, I believe, like O of like n times k. That is because that's because we still need it's bottlenecked by finding how many trees are still active in an interval. So there's a couple of ways to do this. You can one directly just optimize it with data structures. In the past, I think there's been a sentiment generally of like Silver should not have more quote unquote advanced data structures. But given like this contest and also last year, I think like February or something, it's been the trend that like for Silver, you generally want to have some sort of like strong data structures. At least even if not required, they'll make your life a lot easier. A couple of ways to do this. First is of course using a segment tree. You can like take some range sum on your interval to see how many trees there are, or the second is the order statistics set. I've implemented the second approach. We can go over it pretty quickly. In essence, we simply just we simply what an order statistics set is it's a built-in data structure. It's a bit more esoteric. I think there are some code forces blogs that go over it, but what it does is it's a set, but you can also query how many elements are less than a particular value. So with this, we can just run the greedy, but then we can kind of check how many elements are in our interval in log time just by taking this count over here. And then with that, we can just insert trees as we go. Now, if you don't want to do this, we can also have a slick iteration order with a priority queue. To sort of do this, we can maintain requirements of each interval and then use prefix sums to sort of compute the number of trees quickly. Here's a code that uses this. It's a bit longer, but it sticks to more basic concepts. So perhaps this is like what you could think of in context if you didn't know some data structures. The key idea here is that you can maintain a priority queue that just like kind of stores the requirements for each thing, but then instead of maintaining the number that's left, you simply maintain the number you maintain both the number that's left that's like required and also the prefix and also the number of trees that were active when this interval started. Thus, you can use the sort of prefix sums approach to compute how many trees need to have already taken in the course of this interval to do this quickly and not have to run an O of K update on each interval after you take each tree. I know that solution may have been a bit rushed, but hopefully this made sense to y'all. I'll stay around for any questions, but if there are none, I'll hand it off to Andrew to go over the last problem.
Okay, the last problem. Okay, the last problem is conveyor belt. Let me share my screen. So I'll give you guys 1 minute to read like the summary. It's just like you have an n by n grid, and then like you place conveyor belts on them, where they could like move an item left, right, up, down, or the conveyor belt has nothing, or like the spot has nothing on it, so there's no conveyor belt. And then there are queue queries with like updated conveyor belts, containing Y location, X location, and the direction. And you want to output the minimum number of conveyor belts that are stuck. Okay, so I'll be going over the sample input to make that more clear. So that's the sample input, that's the sample answer, and then basically we're gonna go one by one through this. So 11R, it's gonna place it there. The arrow faces right, and then 33L, it's gonna place it on the bottom right, facing left. 32D, it's gonna place it 3 down, and like the second column, yeah, and facing down. And then 12L, it's going on the first row, and then going to the second column, yeah. And then 21U, it's going 2 down and like the first column, yeah. Okay, so basically like what the problem is asking is like how many spots are there where you can place an item and it can get out of the square. So like basically how we're gonna like find that is basically like for this specific sample, we can get out of this square by just like moving out. And then for this square, we can move down, and then this square lets us move down. This square, if we go on this square, we just straight up move down. If we go on this square, we go to the left and then we move down. For this square, we should go right, or you can go left. And then for this square, you can go up or right, right. But like for these squares, they're like stuck in like a loop, right? So like if you start on this square, if you start on this square, you're gonna go to this square. And then you're gonna have to go back here, and then it's just like stuck, right? And similarly, if you like start on this square, you're gonna like go back to the loop. So like basically there's 3 squares where we're gonna be stuck. We're gonna place an item on there. And then essentially how like naive solution, not exactly a naive solution, it would work, but like a easy to think solution is that we have oops. But yeah. So let me okay, so basically like a thing you can implement is that you have like marked squares, and then we're gonna like mark everything outside of this square. Like we're gonna mark it, okay, because like it's like where we want to go, if you get what I mean. So like we're gonna mark all of these squares, and then basically, if you can get to a marked square, right, you can get out. So like since this square like it's empty, you can place it with any arrow. So like we can mark this square, and then this square, it's next to a bunch of marked squares and it's like unmarked, so we can also mark this square. And then this square we can also mark because it can easily get to this square or this square. Oh, yeah. And then this square we're gonna mark because it can easily go to this square or this square. And then this square we can mark because it can go to this marked square. And then the square we can mark because it's literally surrounded by marked squares. And if you notice for the rest of them, you can't mark it because like it doesn't, you can't go to a marked square from like any of this. So this is kind of like a flood fill, like a flood fill. But like if you do it in like, if you do it every query, you're gonna have O of n squared times q time, which is too slow because I think q is up to 200,000 and n is up to 1,000. So that's too slow. So basically, like the smart way to do it is that you start with everything and then you go backwards. So like in this example, we have 3 of these that are not marked, right? So then we look at like the last input, right? 2, 1 up. So like we're just gonna delete that, and then oh, now we can mark this square, right? So now we only have 2. Let me mark it real quick. Yeah, we can mark this square. Why is this so messy? Let me make it less messy. Right here. Yeah, so now we can mark the square after we deleted it. So now we only have 2 unmarked squares. And then we just keep doing that. And then like the time complexity to do the update is actually like really quick because you only need to check like 4 squares around you. Yeah, that's like the solution right here. Does anyone have any questions? Okay, I'm gonna go on to the code. So this is a code. I'll send it in chat after we're done. So basically, first you get n and q, and then you fill the grid with question marks. We're making our grid like a little bit bigger. Like we're making it size. We're making it like too bigger, and then we're putting question marks in it, and then we're gonna like go through all of the queries and then like put all of them in, you know. But then we also have to store the indexes because if we don't store the indexes, we can't go backwards in the future. Okay, so we start our flood fill at 0, 0. And how this flood fill works is that if it's going up, if you get to a square and it's pointing up, we're gonna look at the square above us and then check if it's a dot, and then like if it's marked. And if it's marked, we're gonna make it a dot. If it's not marked, it's obviously just like not marked, right? Like if you're looking above you, right? And like there's and this and it isn't marked, like you're just not gonna be updating the yourself to being marked. So yeah, it goes through up, down, left, right, and then it goes, and then like if it has a question mark, you update because um you're getting to the question mark from a marked square, so you can set the question mark to anything. So like your question mark would just be a mark. But yeah, and like basically for these, it's basically if it's not too big or too small, we just keep flood filling. That's just what. Like the initial flood fill is gonna be n squared. Yeah. Okay. And then now after we do the initial flood fill, like this, we're gonna go we're gonna make a vector of outputs, because like if we start outputting, our outputs are gonna be like backwards. Like if it's like 0 0 0 2 3, our output is gonna be like 3 2 0 0 0. So we have to store a output vector, like output it later. So basically it's just like iterating through the queries, and then basically you say output I is just gonna be like the total number of squares, including your padding, minus like the marked squares. Like escaped is marked squares. Like it can escape. So like you might be wondering like if the padding affects the answer, and like it doesn't, because like the padding is always going to be all marked, and like your total is going to be n plus 2 times n plus 2. So like your padding is just like not going to affect your final answer. And then we go to R, we get RNC, which is like the y axis and the y position and the x position, and then you just like go to all like your directions and try to flood fill. Yeah, and that's it. You just like output after that. Because the flood fill automatically updates your answer. Like we have escaped, and then it automatically adds something to escaped after we get a dot in. Since like our escaped is always getting higher as we're going backwards in time. Does that make sense? If there's no question, I think we're done.
Alright, yeah. Thanks everybody for coming to our 2024 December contest workshop. If you're interested in our next workshop, that will be sometime after the January contest, definitely just like the next week after. And if you just like to learn more, and we also do offer live classes or self-study classes, and you can check those out at joincpi.org. Apart from that, if anybody has any questions, you can stay behind. But we're finished with our workshop today. Thanks to all the instructors for showing up, and thanks to all the students for being a great audience.